indeed. Okay, so I clicked on a dozen or more names. If I missed you, send your name in the chat message. I'll do it right away. Now, where's my markers? I gotta find those. Okay. Red and green, blue and black. All right, are you all taken care of? Is everybody okay? We're going to start. You remember where we left off? Oh man. What was the? Oh yeah, we left off with scientific binary numbers. And before I do that, it's my job. I have to remind you about the announcements. So here's the video. Switch. Oh, hold on. The video is not plugged. The camera is not plugged in. What did I do? Okay. The camera is off to one side. That it. Now it's in. Okay. Come on. Okay. Now we do it. This is a mouse cable. I can't get it out of the way. And then there's extra paper on the side. It's my job to remind you every time. Johnson likes visitors to visit him at 5:15 today. Meeting. And it's not, Zoom number is 886-115-811-34. Okay. Anything else about that? Any other email? Any other announcements? I can't think of any. So don't forget midterm. Near spring break week. It's not during the spring break. It's the day before and the day after. I tried. It doesn't make sense to have the test 2 class meetings before spring break. All of you will just disappear after that anyway. So like if we have class 2 on Thursday and I put the test on Tuesday before spring break, nobody comes to class on Thursday. That's just the way it works. So we have a test scheduled for the Thursday before spring break and one after. So there's concept test and programming test. Different days. Test. Yeah, it's still a week. It's still a whole month away, but it doesn't hurt to start planning now. Plan for it in advance. I've posted the midterms from last semester with the answers included. You can practice that concept test from last semester and see if you pass. You can grade yourself. I would download the test with the answers, but cover up the answers, see if you can solve the equation, and then look at the answers and check your own work. Okay. Let's see, any others? Okay, we're gonna go on. Let me check and see any messages for me to address. Where's the mouse here? There it is. No messages. Okay. Let's resume. This is a material for concept test. You remember that we had scientific binary numbers. Binaries. Last class meeting. And they look like, in principle, they look like 1.011100000000101 times 2 to the 9, or that's the general layout of it. And you should remember, this is called, in modern technical language, that's called significand. And that's called hidden. And the 9 is called true exponent. And the 2 is called the base. I think that's common knowledge. Remember all that? Okay. So we're going to pick up at that point. And here's what we do. We have 64. We have 64 bits to work with. That's our entire register in SSE. 64 bits total. And somebody had to subdivide those as follows. 1 bit is for the sign of the number. 11 bits are for the exponent. And what's left? 52 bits are for mantissa. Or I want to be modern. Got it? Okay. So those numbers add up to be 64 bits. So what we're going to do right now is study how we fill in those 3 pieces: sign, exponent, and significand. How should we start? Let's start with the 11 bits of the exponent. 11 bits. And we pick a special number, or somebody before us picked this special number. The special number is a 0 bit followed by 10 ones. Okay, and I'm in a cold room. It's a really cold temperature here. Okay. So 10 ones. That number is so special that it gets a name. And that's called bias number. And we're going to use it most of the time in binary, but we'd like to know what is it in base 10. So, I mean, there is an answer. It's kind of, you need a calculator to do it nicely. You remember, that's equal to a 1, that's a 2, the next one is a 4, the next one is an 8. Oh, did I do that right? 1, 2, 4, 8. Yes. Doesn't look right. I guess it is. Okay. And that's a 16, and that's a 32, and that's 64. And the next one is 128. And the next one is 256. And that last one over there is 512. And if you add all those numbers together, you'll know what the bias number is. 512, 256, 128, 64, 32, 16, 8, 4, 2, 1. Okay, I'm not going to do it because I did it many weeks ago. It's 123. No, it's 1023. Okay, that's our bias number. But you watch what follows. Most of the time, we're going to use it as a binary form. Okay. All right, so let's learn by example. How did I get this strange paper? Okay, so we need a good working example. How about help me make up something? 133 point. Let's keep it nice and easy. 375. Okay. Now we're going to go first to that. First milestone is to get it to scientific form, and then the next milestone is to go into IEEE form. We're going to do the whole thing this time. 133. So what's the highest power less than or equal to 133? I think it's 128. Yes, 128. Oh, wow, we're going to have a lot of zeros in this thing. That's the way it's going to come out. So this is equal to 1 of 128 plus 0 64s plus 0 32s plus 0 16s. Yeah, how many zeros? Plus 0 8 plus 1 4. And then 0 2s and 1 1, which is written more compactly as 1 0 0 0 0 1 0 1. That's 133. Okay, what about 375? Let's, for practice, we'll do the long algorithm. Okay, let me check, not missing any messages. So far, no. Okay, the long algorithm says you multiply by 2. 0, 14, 15, 6, 7, makes sense. 0.75 times 2, 0, 14, 15, 0.5 times 2, 1.0. And then I take that 0.0 up here and multiply by 2, and it doesn't produce anything useful. I just get 0.0 back again. So we can officially stop right here. The rest of that would just lead to more 0, 0, 0 stuff. Okay, so the fractional part is 375. Does this show up in the screen? I think so. Equals, and those are the bits, 0, 1, 1, 0, 0, 0.1, 0, 1, 1. We could add trailing zeros, but we've got our main answer in front of us. This is the first, second, and third answer. Okay, and you know, if you add a lot of zeros at the end of any kind of fractional number, it doesn't change the value of it. It's still the same fraction. That's still the same as 375 0 0 0. They're equivalent to each other. Okay, let's put it all together. 133.375 is 1 0 0 0 0 1 0 1 dot 0 1 1 times 2 to the 0. Okay, and we're not scientific yet. 1 2 3 4 5 6 7. It's going to have to move it 7 places. Okay, so this is 1 0 0 0 0 1 0 1 0 1 1 times 2 to the 7. And that should look like where we left off last class meeting. I hope it does. Okay. Well, now the next step, that's sort of a pause place. We pause here and look at it. Yes, that's scientific formation. We're in base 2. The next step is we take the bias number that was on that previous page and write it down. 0 1 1 1 1 1 1 1 1 1 1 and add the 7 to it. Okay, so plus 1 1 1. Draw a line and add from little Indian side. See, this is the low value bits and these are the high value bits. So least significant comes first. We add over here. 1 plus 1 is 1 plus 1 is 10. Sounds okay? 1 plus 1 is 10. We carry 1. So this is 1 plus 1 plus 1. That's 11. And carry 1. 1 plus 1 plus 1 is 11. Carry 1. 1 plus 1 is 10. Carry 1. 1 and 1 is 10. Carry 1. 1 and 1 is 10. Carry 1. 1 and 1 is 10. Carry 1. 1 is 10. Carry 1. 1 and 1 is 10. Carry 1. 1 and 1 is 10. Carry 1. 1 over here. Okay. That number is called stored exponent. EXP. And that's good. That's so far we're on track. Then, hey, we're getting close here. Okay. Looking back. Oh, you know, I want to put a red box around this. Remember, that's mantissa, also called significand. And also remember, zeros on this side do not change the value of it. And you remember hidden bit? That's that one. And we have stored exponent down here. So, okay. Now, next step is we're almost done, actually. Isn't this nice? Next step is to write all this in 64-bit registers. Pretend you're inside of the SSE XMM types. The first thing that's in the register is the sign. This is a positive number. Remember, way back here, it was a positive number. So we put a 0. Then you place the stored exponent, which is right here by my marker pencil. Okay, 1 0 0 0 0 0 0 0 1 1 0. Okay, and then you place the mantissa part. The mantissa is in the red box right up there. So let's put it in here. 0 0 0 0. And then it's 1 0 1 0. And then it's 1 1 0 0. And then there's more zeros. Okay. And you fill in a sufficient of them until you have 64 of them. 64 total across the page. Okay. Hey, that is IEEE number representing 133.375. However, for us humans, That's really nice in a register. Move that into an XMM register. The register is very happy. But for us humans, it feels better if we see it in hex form. So this number would be written as 0x. Then up here where my pencil is, that's a 4. And then the next one is a 0. And the next one is a 6. And the next one is a 0. The next one is a 9. The next one is a C. The next one is 0 and 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 0. We're all done. This one is IEEE number. That's a real nice float number that will work very well in your XMM registers. And just to remind you, down here, these two, that's one. Let me say further. 2 digits in hex equals 1 byte. So that's the LSB. These LSB, these significant byte. And this is tricky, but because one of them is the sign, but in principle, that's the most significant byte, MSB. That's what they really call it, even though 1 bit is plus minus, it's the sign. The rest of it is actual number, actual exponent. Okay, and you already know the computer processes these float numbers starting here. It looks at these and it goes all the way on, start here. Okay, now you got the notes. I hope you got the hang of it. That's the process of converting decimal float number to IEEE float number. For base 10, that means decimal. Float to IEEE float. Okay, and it goes through that intermediate step of scientific binary notation. Let's see, any questions? Let me, is 1010 a 10? No. Oh. The answer is yes, but you're doing a trick. No, what are you trying to do here? No, that isn't right. 1010 is 10. Okay, 1010 base 2 is equal to 10 base 10. Okay, yeah, I agree with you. It looks so strange to see 1010 is equal to 10, but it's a change of base that makes it true. Okay. I hope I didn't mess it up and get it wrong someplace else. Okay, on your midterm, there's like half a dozen of these. You gotta be really good at it to get it done in a lot of time. So SI leaders have been instructed to practice this with you until you can do really hard ones. What's a really hard one? I'm trying to think of a hard one. 77. How about that? 77.7. It gets hard because of the fraction. That's where the difficulty comes in. Let's see if 77, you got 164 minus 64. Try this, 1, 3, plus 0, 3, 2, plus 0, 16, plus 1, 8, and minus 8. Now with 5 over here, plus 1, 5, 1, 4. Subtract that off, you have a 1 left, plus 0 of 2, plus 1, 1. Plus 0.7. We have to deal with that in a moment. So this number is 1001101 dot plus 0.7. What is 0.7? Okay, so 0.7 times 2, because I don't know, 1.4. 0.4 times 2 is 0.8. 0.8 times 2 is 1.6, and 0.6 times 2 is 1.2. 0.2 times 2 is 0.4. 0.4 times 2 is 0.8. One more. 0.8 times 2 is 1.6. And I think where are we? We're at the point where I think this is the same as this. Dot, dot, dot. Okay. See those, the first set of calculations is equal to the second set of calculations. So the whole big number is 77.7 is 100111011001110 times 2 to the 0. And there's 1, 2, 3, 4, 5, 6 equals 1.0011110011001100 times 2 to the 6. Okay, now how are we going to deal with this? The exponent is 6, so we have to do an addition. 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, plus 1, 1, 0. 1, 1 and 1 is 10. 1 is 11, and 1 to carry. 1, 1 is 10. 1 to carry. That's 10. 1 to carry. 10. 1 to carry. 10. 1 to carry. 1 to carry here is 10. 1 to carry. 0. 1. 1. Okay, I think we got good results here. So then you put this thing, how can we put this all together? Final answer. 0 is because it's positive. And then this piece right here, 1, 1, 0, 0, is the start of the stored exponent. So it's stored exp. Okay, then the rest more stored exponent. And then more. And then we go up here and you have to focus on that mantissa. Okay. Let's see what it does. 4 of them is 0, 0, 1, 1. And that takes us to here. 0, 1, 1, 0. That takes us to here. Then it's 1, 1, 0, 0. to here. Oh, I see. 1100, 1100, 1100, 1100. And then let's say there's dot 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 here. See, that pattern is repeating. 1100, 1100. And then you run out of bits. You reach number 64 and you don't have any more. So what do you do next? It doesn't fit in the register, but if the register were bigger, it would look like this and keep going. So this bit here is not 0, it's more than half. And so it's a round up function rather than a round off function. So we add it to here, 1101. And now you're looking at the IEEE number. It's this whole thing across here with this adjustment for roundup. I'm going to write it in hex right now. Any questions? You put 9C instead of AC. I did. From the last problem. Oh. Yeah, I see your point. Hey, everybody, that is just a bad. I had a dead brain cell for a moment. That's not a 9. That's an A. Thanks, Mom. That's very true. We better fix it right now. In case you're recording this and you play it back, you'll wonder why that 9 is there. That's an A. Can you see that? This is an A. And then those are C. That's a C, and then zeros. Oh, thanks. No, I like accuracy. It's okay to tell me when I mess up something. Okay, watch this one. I don't mess this one up. Okay, we're going to go towards hex next, starting here. Okay, this is the marker that says hex is coming. Okay, that's a 4, and that's a 0, and that's a 5. I'll be more careful. And that's a 3. And that is a 6. Let's see, I'll put it right above it. There's a 4, 0, 5, 3, 6. Next comes C. Next comes C and a C and a C. And I should count these off carefully. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. But number 16, the last one, is D. Okay. And there's supposed to be a little space in between here. 4053 space 6C C C C C C C C C C D. Okay, there. And this all came from 77.7. Okay. Now, I'm going to look for the little program that see if we can confirm this electronically. Let me put the cap on the marker, and we're going to. Oh, I got to find it first. If I can find this little program, then I'll share the screen for you. Just hang on, everybody. Don't go away. Windows F. So I'm going to find this piece. and I don't know where it is. Yeah, I don't know. See, I can't find it. It's gotta be here someplace. Yeah, no, I found it. I think we found it here. Okay, so okay, if open the terminal. So I'm gonna share the terminal with you. Move it to number 4. Okay, we're gonna get this right. Okay, share screen, terminal. And I think you can see, oops, no. Okay, I wrote a program a year ago here, ls-l, and let's run this, shrun.sh. Okay, so it says enter a number in decimal. That's 77.7. 77.7. And get an answer. Now, do you notice? See it's kind of red color characters. You see that number? You see the last character in the letter in the number? It's a D. The machine knows what to do with that round off problem. Okay, so it says 40536, and then a whole bunch of C's until it reaches D. Is that the number that we computed? There it is, 40536, whole bunch of C's and a D. So yeah, it is. Okay. Now, there's some curious things. It also tells us that the machine in 64 bits can't show us 77.7 100% accurately. It's off by this 0.3 of a trillion part, see. And if you're using 32 bits, that's the middle line, it still can't show you 77.7 100% accurately. It's a little bit too small by a small amount. And if you're using 16-bit floats, which are not common, but they exist, then you're off even a lot more. Here's the hex number for 16-bit 7.77. Here is the 32-bit hex for 77.7. And here's the 64 one. And I did this to point out the rounding up at the end of the expression, it becomes a D. Okay, so is there anything else to gather out of this? What was the one we did? What was the number we did just 20 minutes ago? I'll find it and then we'll put it in. It was 133.375. Okay. 133.375. Not that. We did that right. Okay. And here it is in the middle. It's 406 AC. And on the paper, I had made a mistake and called it 9C. It's really AC. And the machine says, agrees with that. It's an AC. Okay, so let's remember back here. I made that correction. It's AC and not 9C. Okay. Well, so on your midterm, there's a 3 or 4 problems to be solved of the nature we just did. And you should practice it so you don't stumble around and forget what you're doing on the day of the test. I've talked with the SI leader. He says he's going to practice these. I don't know when, but he promised soon. And what did we learn out of this? We learned some names. Stored exponent, true exponent, and bias number, and poor old hidden bit. Did you notice what happened to him? If we go back and look at calculations, where was it was, I'll bring it back. See, the red arrow is pointing to the hidden bit. You notice he gets forgotten. It never gets included in the rest of the calculations. The whole process goes on, and the one bit gets left out. But you know what? The electronics are programmed to handle the one bit, even if he's not there. So some people say it's hidden. I say it just gets left out of the, it never gets stored in the register. But yet when you compute with it, it will perform as if the hidden bit were present. Okay, so now you know hidden bit, and we need to make a number line. Okay. I think in math class, they sometimes talk about the real number line. So in computer science, we have a real number line. 0.0 is the middle. It goes positive this way, negative this way. And on this number line, somewhere very close to 0, there's a special number called, I can't write, I'll write it up here. Smallest positive normal number. Positive normal, or NOR, MAO number. Okay, so it's here. And then all the stuff to the right are the normal numbers. Our 2 examples today are normal numbers. Normal numbers. Okay. And then you get hit to a certain point, really large, astronomically large, and his name is positive infinity. But there's still some stuff higher than infinity. It's like you reach the farthest galaxy, but there's a little bit more just beyond. And those are called the nans. Okay. And you can't calculate. You can put nan in your register, but if you try to multiply it by another ordinary number, it won't work. You can't add it to another number. It's, as far as instructions go, it's just dead. Okay, negative wise, this same number here, if you put a minus sign in front of it, you're on this side of the 0. And so it's the mirror image. That's what I'm trying to explain. This is a mirror image of that smallest positive number. So it's negative smallest positive number. And then there's a big region of negative normal numbers. Negative normal. You just take one of these and you change the one bit at the most significant side, and you change it from 0 to 1, and then it flips it over to this side. So if that's true, we can also flip positive infinity over here, and we have negative infinity. And then over here we have negative nans. And then finally it all ends. And there is an ending point. So how's our clock going? We're at 2:48. I hope to, I'm not going to talk until full 2 hours. I want to leave time every lecture for just open discussion of programming issues. I want to hear your bugs, hear about your bugs in your programs, and I'll give you my best knowledge to help you remove those bugs. Let me still write on this. So in a few minutes, we'll get there. The question here is, what is this one in base 10? Well, it's even worse. Before we even get there, we should find out what is positive infinity in base 16. Okay. So you can't store in your program or in the computer any number larger than, I didn't say that quite right. Yes, you can store larger numbers, the nans, but they don't do anything. You can't add to them, you can't subtract to them. You can try to ask printf to output them. Now, printf will just simply output, in the case of infinity, it just outputs the 3 letters INF. In the case of nans, it just outputs the 3 letters NAN. So we're going to find the upper bound here. So how does this work? To get the largest number on the number line, we want to make the exponent as large as it can be. Okay, so here is, okay. Let me do a binary first. Okay, it's positive. So there's a first 0. And then we make the exponent as large as possible. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. There's 11 digits, 11 binary bits in the exponent. Okay, then comes, there's an imaginary dividing line here. Then comes the mantissa part of infinity. But we don't want mantissa to be so large because the nans that come after it are going to have those values. The nans are going to have zeros and ones and zeros and ones out here. But infinity just gives a bunch of zeros. Okay. So we can answer the question right now. What is plus infinity in IEEE form? And here it comes. It is 0x. Let me put the chat bot messages aren't in front of me. Okay. 0x. That's a 7FF. Okay. And all these are zeros. "16 digits completely. It takes 2 digits to make a byte. So 16 digits means 8 bytes. 8 bytes means 64 bits. 64 bits means 1 SSE register. Okay. So this is one thing. Okay, now in the last half hour, you saw the process of going from base 10, from decimal to IEEE. We have to reverse that now. Decimal to IEE. Okay, that was the problem of 77.7. We started with 77.7 here, and did all the work and got IEEE. Now we're going to reverse this and go the other direction because we have IEEE right in front of us. Okay. I'm going to go to the next sheet of paper. Okay. Well, there's a bunch of boxes here. I don't know that. Okay, so out of this IEEE, I'm going to take apart this part right here. The 7 is a 0, 1, 1, 1. The F's are this and this. Okay, this one drops away because that tells us it's positive. This one is the stored exponent. In the previous problem, we add bias number plus true exponent gives us stored exponent. To reverse it, we take stored exponent minus bias number, and we'll get the true exponent. So here we're going to do it. Minus bias. I can't do this right. I'm sorry, everybody. Let me try again. I'm going to subtract the bias number. 0. It's 10 ones. Equals bias number. Okay. Draw a line and subtract. And this is easy subtraction. It's 1 from 1 is 0, all the way down the line. 1 from 1, 1 from 1, 1 from 1. 1 from 1. 1 from 1, from 1. The last one is 0 from 1. Okay, and what we got was true exponent. Okay, but it's in binary. Now the question is, what is that in decimal? So, but that's not hard. Starting at the least significant bit, this one represents 1, of which there's nothing. 2, 4, 8, 16, 32, 64, 128, 256, 512, and then comes, what's the favorite number of all computer scientists? It's that one right there. You don't know? Did your teachers tell you in the past? The most favorite number of all computer scientists is the one they bet all their gambling on is, oh, that's right, Richard. That number 1 is in the position of 1024, and all the others are wiped out. So the true exponent is right here. That's the number we all dream about, is 1024. Okay, so now we're making progress. At the same time, let's find the mantissa for infinity. Here it is. It's this piece. All zeros is the stored mantissa, but don't forget the hidden bit got left out. You can't lose him. So the mantissa part is, and I'm not using the language exactly right, but I think you'll understand. There's hidden bit, and then all these zeros, 52 of them, times 2 to the 1024. Okay, so you can see the pieces are all there. Here's hidden. Here is mantissa. Here is true exponent. And now we can simplify it mathematically just a little, because 1 point, a bunch of zeros is just the 1. This equals 1 times 2 to the 1024. And 1 times anything is just that anything. Okay, we have an answer. Okay, that's it. 2 raised to the 1024 is beyond this, is the next number beyond any number we can compute with. 1024 is infinity, and that begins the nands. 1020, this number is part of the nands. So in the number line, you can compute with all these numbers all along here, but when you come to infinity, that starts with the numbers that you can't compute with on out to about here someplace. Okay, so infinity is one of the nands, and it's the starting point where all the rest of the nands appear. Okay, I think we're going to pause here. Does anybody have a question about any of this? No or yes? In 64-bit IEEE numbers, we're going to talk about programming in just 60 seconds. 64-bit IEEE numbers. There's a limited amount of precision, limited amount of accuracy. You don't get every single number perfectly represented. Every single number of the mathematical number line is not represented in the IEEE set, but a lot are. So IEEE numbers lose precision after about 17 digits, 17 decimal digits. RECISIO. After 17 decimal, I'll explain that more clearly. Decimal digits. So if you had a number, 1, 2, 3, 4 in decimal, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's a 5. 5, 6, 7, 8, 9, 0, 1, 2. Okay. You get fairly good precision out to about number 17, more or less. 1, 2, 3, 4. That's right here. In this area. This can be represented accurately. All the rest is considered electronic garbage. And even if you input that large a number, it will only be able to manage about that much of it. In fact, let's do that as an experiment for the last case. See if this works. And then I'll ask about programming. Now, buddy, I'm trying to share this. Where share screen? Okay. Okay, let's run the program. And it says enter something. Let's try, I don't know. 1, 2, 3, 4. When you count decimal digits, you count both sides of the point. 5, 6, 7, 8, 9, 0. 1, 2, 3, 4, 5, 6. That's about the break place. 7, 8, 9, 0, 1, 2. 5, 6, 7, 8, 9, 5, 6. It's losing the 7 back here and going off into garbage land. So yeah, that's true. See, it got those numbers accurate. 1, 2, 3, 4, up to 16th place, but the 17th place, it lost some of the precision, and it's just random junk beyond that point. That's all I wanted to make out of that control. I'm going to close this. Control D. You know how to close a terminal window from the keyboard? Control and a D closes the whole thing. Okay, class, we're done a whole hour on that. Who has programming issues that I can help with? Or it doesn't even have to be specific to a program that you're working on, just general knowledge about this programming language. Yes, I know you can post your programming bugs in Discord and you'll get an answer eventually. But here I am ready to help you with anything that you're currently working on. Is there anybody that I could answer a question about that we can all learn from? Nobody has a question? Tell me, your program is compiled the first time? That's really amazing. I can't do that. You have no bugs. Well, come on, you guys. I'm counting that on the programming test. You all turn in perfect programs. They just run right through the test data like nothing. And because we do have a programming part of the test on a second day. So everybody can validate an input as a true float or not. Validate inputs. One of the assignments is validate your stuff. You know that you put the incoming number. So you write software not for yourself. At your corporation where you have a career, you're part of a team of software developers and you write programs for other people to use. And some other people are real idiots. It says input your float number, and then this idiot holds down the 7 key for automatic repeat, and it inputs 7 85 times, some stupid thing like that. Okay. Well, or holds down even worse the W key for 20 times, and it's not a valid input. How do you catch that input? Everybody's already solved that. Could you start using jump for errors? Sure, Charlie. Let's go in that direction. Like you input an input that's obviously junk. Input 3T.65. We want to toss that out as an error and not accept it. You're inputting the sides of 2 triangles or whatever you're inputting. This is just not a float number, okay? Nor is something with 2 points, 37.8.72. That's not a float number. You're only allowed 1 float number. Okay, so the strategy is to have scanf take the input from the keyboard and put it in an array of bytes. Careful, we need an array of bytes. What segment is that? That's segment BSS. Segment BSS. And you declare, I'm going to give it a name, keyboard input, key input. And RES B, how about 100? Okay. And then that's probably enough. Let's say we're going to input this number from the keyboard. So a comment on the block would say get input. We don't know that it's a number. It might be just string of letters. Input from keyboard and store in key input. Okay. Move, here we go. There's a block. Move RAX0. Move string. I'm writing too fast. Sorry, everybody. Move RDI string input, string form. Move RSI key input. Okay, we're ready to call scanf. Now, why do I know that? It's because if you, this is a side visit. If you look in online for a full definition of scanf, especially you want its prototype, it will show you, I believe there's an integer return, SCANF, and it will say that you have a string here, and then it will say we have a pointer here. In our case, it's pointer to string. That's a string, char store, like such. Okay, so this is going to be like %s, and this will be like a p or some. For us, it's key input. There's our pointer. So pointer p, and then calling scanf inside of a C++ program, you put that and you put that, and it will take the incoming string and put it to where p points. Okay. So I look at this and I know this is RDI and this is RSI. Those two are always in that order. Okay, there's RDI, RSI. I can call scanf. And it's put the string in here. Let's put a circle around it. The string has now entered this place. Okay, what comes next? We'd like to find out, is that really a float number or is it a bunch of garbage? Okay, the answer comes from the function isFloat. What does it return? isFloat returns a Boolean. And it accepts one parameter, which is a string parameter, an array of char parameter. Okay, so one parameter means I only use RDI, and I can expect an answer in RAX. Okay, let's set that up. So we'll say, to start the block, we'd say set up to call isFloat on key input. Should be on one line, but one more space. Okay, here's the setup. There's no XMM registers involved. Move RAX 0. Okay. Next, Remember, there's one parameter for his float, and it's the string itself that's key input. RDI key input. That's the name of the string where the data is stored. That's it. I guess it's time to call is float. Okay. Bool is simply an integer of where the values are interpreted as 0 means false, non-zero means true. Okay. So since it's an integer, it's inside of RAX. Let's save RAX in a safe place. Move R14 RAX. You've probably heard me, or you've heard the discussion that RAX is considered volatile. It has many, many uses. R14, R13, R12, R15 are considered stable registers. So I'm putting a copy into R14 because R14 is a secure place, and we'll say that, I wish I'd put it underneath there. A note to yourself. Let me get useful paper here. Okay. R14 holds the outcome, the return of is float. Is float. Okay, next thing we have to do an if-else statement on R14 to decide if it's a false return, meaning it failed the test to be a true float number. Then I'm going to suggest you just put out a nice message to try the program again, and you quit. Okay, so let's do it here. Here's the block coming, block of code to, what are we going to do here? We're going to keep number, input a number, or exit from the program. Or exit. Okay, someone's going to say, well, but why don't we just loop around and give the user another chance? Yeah, yes, that's just very fine. I don't want to build a loop right now. Let's handle it by terminating the program gracefully, and the user has to restart it. Okay, so here it comes. We compare CMP R14 with a 0. And 0 means it failed the test, or it's false. It's not a float, it's false. All right, so if equal, then we should go someplace else in the source code and display the message, bad input encountered, try again. Okay, so I'll call it bad input. All right, it's way down here someplace will be bad input, but we'll fill it in pretty soon. So if it's good input, then it goes straight below here. And then here's a block of code to convert that good input into a real float number, because right now it's sitting there as a string. Block to convert string to be very precise, to 64-bit double. It's more than float. Float is a very generic general name. It's precisely, it's a 64-bit double. Okay, so what we're going to use is a built-in function that's part of the C++ library called ATOF. It returns a double. And it accepts as input a character array, char, like such. That's its prototype if you were using it in C++, but we look at it and say, that's one parameter. It's going to be RDI, and we can call it. Okay. GI, comma. Okay, that one parameter is in fact, it's a key in, is that the right name? Key input. Okay, very short, one parameter function call. So we call ATOF, and remember, it produces a double. The one place it puts the double is XMM0. So we have an answer. It's stored in XMM0, but again, the 8 registers with 8 XMs with low numbers, XMM0 through XMM7, are considered the volatile registers. So let's save this in a safe place. Move SD XMM14 XMM0. The high numbered registers from 8 through 15, it's not perfect, but they're considered more stable, highly stable. 99% of the time, they don't change their value. So this is a safety margin. This is safekeeping. Safekeeping. All right. Okay, what about the case where I have to go back to that if else? Because the original question was what to do. Okay, so scanf, and then you call is float, and then you save the result of in float is float over here in R14. And then you check R14, are you 0? And then if that's the case, you jump ahead. That means it failed. It's not a float. You jump down here to bad input. And if it is a good number, you go straight ahead. So I'm going to place down here bad input. Now with a colon. Okay. And now here you want to put a simple message. We'll do it with printf. Move to RAX0, move to RDI, bad input message, call printf. And when you're done with that, you're under this plan I'm outlining here. After that, you go to the bottom of the code and start popping all those registers. JMP to exit. Okay. Now, so this is like an if-else statement here. Here is the else, and here is the if. But we don't, after executing this one, we don't want to continue straight through and execute this block. That would be kind of dumb to have a good processing and then give a message that you had a bad input when you really didn't. So we need in the middle here is a jump, JMP, to a continue place. I'd put it here. Home. It's okay. So we're almost there. And okay, so if that first number was a good integer, a good float number, it processes this here and jumps to continue. Okay. Continue marks a block where you're going to input the next side of the triangle or some other, whatever happens next in the problem you're solving. The exit is near the end. Exit, and it has a colon after it. And let's see. Do we have to return something in this big function? What we want to get to is all the pops. POPF, that's pop flags. POP, R15, POP, R14, and all the way down, pop, RBX. He's always last, and RET after that, POP. Okay, so if that was bad input, notice how it takes you to, no, I think I did something. No, I did it right. If it's bad input, the compare statement here, and it's bad, it sends you to bad input, which is right here. It gets put out a message that says try again, and then the command right here by my finger, jump exit, takes you all the way to here, and the program is starting to terminate, or it's starting to return back to the caller. Okay, if it was a good input, then the compare back here doesn't send you far away, but it just lets you fall through and continue processing. The good, you have to translate that input string into an actual number. So you go through this and this and this and save your actual number someplace. And then in logic, you don't want to execute the bad input message. You want to jump over it. So it takes you across here. And now you're ready to do something else. Input the second number, or whatever you have to do with this. Input second float number. Okay, and then you'll process all this stuff, and then eventually you come to here, and you pop all those R-type registers, just like in the case of bad input. Oh yeah, that's a long answer to a question about what to do with errors. You have to implement an if-else statement, and it doesn't look pretty in assembly. If-else in C++ actually looks readable. If this thing, variable cost is greater than 100, then you're going to do this piece, else you're going to do this piece. And it's blocked off with braces. Brace, 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 brace. That's easy to understand, and it's easy to visualize it. See, assembly has the same construction, but it's not pretty to look at. This is the then block. And this is the, did I say that backwards? It doesn't matter. No, actually, very precisely, this is the else part of this compare. And this is the then part of the compare. You've got to be careful with your pointers that you only execute one of these two blocks, not both. And I think it's set up properly for that. Okay, everybody, did you follow all that? So make some summary opinions here. What do you need to test numbers for validity? You need a global declaration. I did it again. You need an extern declaration, ATOF. You need another extern for is float. This one is part of a known library. I'm 100% sure of that. This one might be in the library, but I think the students made it a semester or two ago, and it should still be posted. Check to see if it's in a library first. I just don't remember it precisely. It may be a library function. Library functions are those that you get into your C++ program by lots of includes. You include a library that contains 10 functions. IOmanip. It contains a whole bunch of functions within it. Those functions individually are library functions. This one absolutely is a library function. This one, I'm not sure where it is. I think it's student made, but I won't be sure. I don't know for sure. Ask the TAs, the SI leader probably can direct you to it immediately. So those two need to be at the beginning. And when you compile this function that we've been dealing with, saying that something's extern, let's go back here. See here it's going to call that ATOF. The purpose of the extern statement of ATOF is to tell the compiler, or in our case, the assembler, when it sees this, don't panic and give error messages saying ATOF not found. It's saying, just leave it alone. It's an external function and it's going to be brought in by the linker. Okay. Same way when you call is float. Where do we have is float? It's lost my place. It's way back, another page earlier. There it is. Same story. It's to say to the assembler, don't panic over this thing. It's okay. It's a function that's going to be provided at a later time, specifically at the time of linking. Then when you call the linker, it apparently, as far as I can tell, it looks at the source files and finds all these calls. It says, oh, an external one. I have to find these. Yeah, I can explain. It has to. That linker is pretty smart. It looks through all the libraries that it knows about, both C libraries and C++ libraries, and finds this function. Suppose this is not in any libraries. Then what does it do? It looks at your group of .o files to see if it's there. Can you follow that? Suppose isFloat is not from a public library, just somebody loaned it to you. So then you have a function, isFloat .cpp, and it defines what isFloat does. It returns bool isFloat Oh, the whole bag of tricks is here. And there's some statements here and the whole thing is defined. Okay, so when the linker comes along, G++ hyphen M64, and then hyphen standard equals, we're compiling, we're linking. Standard is C++ 17, and then hyphen O is, we need a name for this, triangle. Dot OUT, and then comes a lot of O files like main.o and get array, I'm making up things, array.o, and finally there is float.o. And then so you list all the .o files in your program. So now the question I was answering is, you're linking this program, and when it comes to ATOF, this linker, you notice there's no ATOF.o. It's not mentioned. It's in a built-in library, and the linker is smart enough, it's been programmed well enough to look in all of its libraries that it has access to and find any missing functions. For those that it doesn't find the missing function in a library, it expects to find it among this list. And these are ones that you've compiled yourself to create object files, and you're providing them to the linker to satisfy all those externs. Here's the extern. It says it's coming later. Well, the linker is coming later, and here it brings it in with it. Okay. There's a slight difference between a only in a very this is like a library file, but it's under your control. You have to provide it yourself, whereas G++ linker knows about standard libraries that already exist. That's the best way I can describe it. This one is a standard function out of a standard library that already exists. Okay, I talked too much. How to set up A2F in C or C? If it's going to. In C or C++. Yeah, right. Yes, you can do this whole program in, say, C++ only, and you'll need to include something. Include, and oh, I don't have it here. I was going to look it up for you immediately. We need to find the library where ATOF is stored. And that's what you'd have to include. And then the program that you're writing below that is set to go. It's able to use ATOF. You can do a web search for that. Where is ATOF stored? I don't know the name by memory. I'm here in my office. I could almost find it. If I'm lucky, I can find it in 30 seconds. If I'm not lucky, it would take 10 minutes. Let me see your question. How to set up ATOF and his float in, okay. Okay. One is you need the library name for A2F in the same way that include math is the library, and that gives you access to those trig functions. your program can now call sine, cosine, and tangent and log and so on. Okay, so you include one library name, which is a collection of library functions. Okay, we need to look up what is the library name that includes ATOF. Okay, after that, oh, and then you asked me about what about is float? That's not, let's pretend for sake of discussion, it's not in is float. Okay, so here you're building a program, integer, main, whatever. And somewhere in here, you want to, you have a string, char, in string, 75 characters, and you call scanf. It would look like scanf quote percent s quote inst. Okay, so you've got an input string, and then you want to check, is it float? But is float is not in a public library, it's one that you made. So at the top of here, you put int is float, and it needs a parameter passed to it, which is of type C string, and it looks like that. So you put a prototype of the function you intend to call, and then integer k equals is float. What's our string's name? It's inst. Okay, now we have an answer. It's if it's a real good string, this will be a non-zero number, and if it's a bad input string, this will be a 0. Okay. So it works in C++ just well. Now this would do we know the library of scanf? Let me I think it might be in standard. I'm looking at short resource everybody. Give me 20 seconds. I know where this one is. I'm close. Where's this thing come from? Oh, well, this one, I don't know if that's got to be right. What I just looked at, and it said that it's in include standard IO, include pound sign stdio quote. Standard input output gives you access to scanf and printf and fgets if you're writing it in C++. If it's C++ only, you're supposed to use angle brackets, like pound sign include. Was it stream IO? Or I forgot it. Okay. All that, it doesn't mean much, but all it simply means that if it's angle brackets, it's in the C++'s own library that C doesn't know about. If it's in quotes, by the way, it has to have an H on the end. If it's in quotes, it comes from the C language library. C++ can use both of them. It's not a problem. All right, so if it's a function that you made, you put a prototype at the top like this. If it's a function somebody else made, it's an include statement like that or like this. And then you have access to all the functions of that collection. Well, we cover a lot of stuff. He says, cool. Okay, well, I think is standard lib. Hey, that sounds right. ATO. ATOF, yes, correction. Yeah, your classmates is, I think that's right, STDLIB. Pound sign include STDLIB, like so, dot H. I keep forgetting H. Okay, isn't it clean how nice it is in higher languages? I showed you in assembly. These three statements take about 15 statements in C plus in assembly. I'm sorry. In C++, it looks so nice, but in assembly, that expands out into a whole can of worms. But that's how we have to live. I went through it earlier. All of this stuff has to be is the complete expansion to assembly. And how are we on time? We're getting close to the end. Let me, just for clarification, you know, in C++, you have a statement like D equals SQ RT A squared plus B squared. Whatever, you have a statement. It looks pretty, we all understand it, it's easy to read. What assembly has to do is to break that down into at the instruction level. The instruction level is one thing that can be executed in the arithmetic logic unit. Okay, this is very complex. It has to get copies of A from somewhere and put it in the arithmetic logic unit with the command to do a multiplication, and then save that, and then do the same thing for B and save that product, and then add those products, and then get the square root of that. That breaks down to many atomic statements. So when we're doing this in assembly, we have to ourselves break it down to the atomic statements that are one-to-one match to what happens in the arithmetic logic unit. That's what assembly is doing, is trying to find an expression for all of this that forms a block of code, and each step within the block of code is not a statement, it's an instruction. And an instruction is one thing that can be executed before it can go on to the next one thing. It's the smallest thing that actually executes. So that's what assembly is doing with when it's an instruction, not calls. Calls is a different story, but individual instructions: push, pop, add, mul, div. Those are all individual instructions, and they have a code number, and that code number forms an instruction in your executable file. So just making it, trying to clarify why assembly is so long. It takes individual statements and breaks it down to atomic level. There's no subdivision, any further refinement. And then you execute those, you as a human person, you put them in a program, and the arithmetic logic unit will execute them in the order that you placed them there, including jumps. Okay. For a midterm, do you want us to make the driver in C or C++? How about I throw it? I'm leaning towards just throwing it open. You, as each individual, choose your favorite. Some transfer students tell me they can do better in C language, but most students who did all your beginner work here at Cal State Fullerton say that C++ is easier. Right now, I'm leaning towards you choose your favorite. Okay, good. Good, Greg. Okay, class, the clock is quickly running away. I'm glad you stayed to the very end. Why don't you, if you got the time, yeah, go talk to Johnson at 5:15. He needs some, companions there. He needs somebody to listen to him. Ask him the stuff about including files and libraries. He needs some work to do. All right, so have a nice evening, everybody. I won't see you for 5 weeks, 5 days until next Tuesday. And watch the website. You might see a new program appear soon. Okay. I'd like to have a solution if the second or third or so on a keyboard is also bad. How are we going to jump back to process? I can visualize it in my head. I really can. You have 2 numbers to verify, or 3 numbers. Let me see. This is the first number. It looks horrible mess. Okay. Let's see. How did we? Oh yeah. And if it's bad, no, that's all right. Oh, if it's a bad input, you jump to here. There it says bad input. Okay, and then you go to exit. Now here you would, inside of here, you set up a scanf to get a new number. Let's see. You call is float. And according to that, if it's a bad one, let's see. Yeah, you can use the same block. If you have to go through that CMP and then call this same block. Oh yeah, you call the same block again, and then after you go to this exit. And if this is a good one, then you do the convert, call ATOF, and save your number in a XMM register. Save number. This is so messy that I'm embarrassed to save the number. I'm embarrassed to show it. Maybe it could be diagrammed better. Yeah. See, I haven't planned this, so I'm sort of like, I have a visual idea what to do, but let's see if I can. How can I do this? Validate the inputs. I'll give it a quick shot. We're running out of time. So your flow of control in your program is running along, and you do a block to scanf a number. Okay. Then you do a test. Is it a true float or not? Is it float? If it's a yes, you go out here and scanf another number. And then you do a test. Is it a float? I think it is float. And I don't want to, well, we could do a third one, but it's going to get a messy diagram. If it's not a float, then you go down here and you error message, ERROR mess. And from there, you go to pop registers. And then you return. RET. Okay. So if this one is a float, you're supposed to go on, and if it's yes, you go on to a new scanf. And then you test it. Is float. And if it is, this is a yes, then you solve the triangle problem. Triangle. And after solving the triangle problem, you go back and you say goodbye. But if this is false, you want to go over here and join this line. And if this is not a float, you want to go over here and join this line and go through the error message. So there's the layout of the logic. It just, it's a real puzzle. It's a jigsaw puzzle. You put that into assembly so that your flow of control is, if it's a positive yes, you go on to good stuff. And anytime that it becomes a false, you go to the error message and then pop registers and quit. Now you want to repeat, give the person another chance. That means after error message, you don't go down here. After error message, you'd go back and get another scanf. You take the person way back there, rather than my easy solution is you just get out. You get out of the program and shut down. The person has to run it again. Okay, you're gonna have to work on that. It's a tough one, but it's doable. If you can visually see where the execution is going to flow, that means it's doable. Just build it very, very, very carefully, and you'll work. Do we have any solution to do a loop for it auto use those if else blocks from above? Okay, it's cool. Thank you. Okay, come on. I'm counting on you solving this in real program code. I never said this this whole language was easy. I never promised yet. I just said it's enlightening. And there's lots of jobs out there that go unapplied for because people shy away from assembly work. Oh, he'll try it. Okay, very good. Okay, everyone, have a nice weekend. I'm glad you're all here. I'm having fun. I hope you are. So I'll talk to you later. I'll tell Johnson he's got a lot of hard questions coming. Okay.